I read this title when I started writing my talk, I got very scared of having to try to summarize 20 years of statistics in our field. So I thought I wouldn't try to be exhaustive, but rather to pick up, I think, few ideas or methods that have been very influential in the way we look at data, or that have influenced me a lot, and then to think about the current limitations and how we can move on from where we are. So just to give you a timeline, I started my PhD in 2002, so 11 years ago, not exactly 20 years, but I was definitely born in 93, looking at these statistical methods, and I think it has been a very exciting era. We've seen the emergence of a lot of new ways to do inference, either imported from other fields or developed in our field, and clearly supported by an explosion in computational power. And overall, it really has offered us, I think, a lot of new opportunities to revisit past or present data, and also to do more with the data we have. So it's going to be a personal perspective on the approaches that have influenced me the most, the successes and failures, and where we can developments that are needed to move on. And so I think we've seen an increase in the number of statistical methods that are available in our toolbox for inference, but it hasn't just been a quantitative increase. I think we are also now better equipped to know which method should be used in what kind of circumstances. So sometimes you have methods that were great to look at detailed outbreak data, and not so great when looking at time series. And I think we understand these nuances better now than before. So in our journey back in time, and at the start of my PhD, I think these are maybe some of the first papers I read in that field. So introduced by Gavin Gibson and Phil O'Neill, introducing Markov chain Monte Carlo sampling and data augmentation in our field. So MCMC are very powerful algorithms to explore complex likelihood surfaces, also to easily derive credible intervals. So that was a useful addition to the field. But I think really the breakthrough here was really about the fact that they provided a very nice way to handle missing data, which is always the big problem when we look at data. So different examples. So here, that's an epidemic. Gavin Gibson looking at transmission of a virus in a tree population. And so the different colors represent trees infected in 1 year, and so white might be 81 and black 82. So very incomplete information here on the time when trees were infected. So from that, very hard to write down the likelihood. Other kind of problems of missing data are when you look at final size distributions in households. So you have the number of infections in the household, but you don't know who was infected by whom, or who was infected in the household or out of the household. Other kind of common problems are on bacterial carriage, where you have swabs collected in schools at irregular intervals. A child was colonized at a certain time point, but you don't know exactly when colonization started or when it ended. So in all these problems, and you have thousands of problems of that kind in our field, it's very hard to write down the likelihood, because just we miss a key piece of the information to make the calculation. And so the idea behind data augmentation was just to say we have these things that we miss, for example, the times when infections start, and we are going to consider these as nuisance parameters, augmented data, and then carry around and introduce a very nice three-level hierarchical model to have a very coherent way to deal with these augmented data. So you have the prior level that it's in a Bayesian setting, so you're defining the priors of your parameters, transmission level describing the latent transmission process, and the observation level ensuring that augmented data are consistent with the observation. And so you explore the joint posterior distribution of augmented data and parameters by Markov chain Monte Carlo sampling. And really, so these methods are fantastic when you have very detailed individual data. So for example, a school outbreak in Pennsylvania, we know who is sitting where, the activities they played, which child is in which class, what are the social networks. If you want to do a coherent analysis of the whole data set, these data augmentation techniques work perfectly. And I suspect we are not going to do better for that kind of data than data augmentation. So the current big limitations with these techniques are for model comparison, in the sense that we don't have the likelihood of the observed data is not available. So we cannot derive deviance information criteria for model comparison. And often we are not just interested in estimating parameters, but also we want to compare different model structures. So that's, I think, one of the major current limitations of these techniques. Sometimes you can do reversible jumps. So in your MCMC, you jump from one model to the other. But you can only do that when you have very closely related models. So it's not something you can always, an approach you can always do. So in terms of future developments, I think we should have a closer look at the ongoing research done in model comparison, where they are trying to build bridges or paths between the different models. So here's, for example, you have a paper in GRSS-B by Friel, where you change your what they want is to estimate the marginal likelihood, so the probability of the data given a specific model. And the way to do that is to basically to look at a series of models parameterized by a parameter t, and so it's just, you see a power posterior model, and they show that marginal likelihood can very well be approximated by an integral over these distributions. So it's very computationally intensive. You need to do basically to run MCMCs for each, for plenty of values of t, but these approaches are supposed to be able to deal with augmented data. And Phil O'Neill, I think, is working on some related ideas, also a bit different. The other limitation we have now with these techniques is in terms of how do we validate the model. So we can obviously look at how the model simulations fit to the data, but can we do better? And here, I think so. Gavin Gibson is doing some very interesting research where he's looking at all the expected distributions of all these latent variables, augmented data that you have in these approaches, and so comparing the expected and posterior distributions of these latent variables, and from that deriving some formal statistical tests to say whether or not the model is adequate. And so just because it's working so well with all these data where we have detailed individual records, you can think, what would it do? What would be the performance looking at epidemic time series? And we looked at that some time ago, so looking at measles in London. And then, so where here the augmented data would be the number of the true number of cases 1 week, for example, and the observed data would be just a proportion of that, for example. And for that specific kind of application, it doesn't work very well, and really that's expected because you have a lot of correlations in your augmented data. If you want to change the number of cases at week t, clearly that's going to affect what's happening at week t+1 or t-1. So chains take a lot of time to converge. And also it doesn't really solve the problem of trying to find some you still need to find some analytical approximations for your likelihood. So you're really stuck to use relatively simple and analytically tractable model. So that's really in the category, I think, tried but failed. And particularly so when you compare that with performances of sequential Monte Carlo algorithms. And I think the first one who introduced that kind of approach in our field, or at least the one that had the biggest impact, was Aaron King and Ed Yonida. So they showed basically with these techniques you can really fit any kind of compartmental model, any kind of complexity to an epidemic time series. And what's so great about the approach is that you just need to have a model of the latent transmission process you can simulate from, and you can always simulate from any model, and then an observation model that relates the data to this latent process. So for example, if your simulation process says you had that number of cases that week, then the observation model could just be a binomial where the number is the of cases is the number in the simulation. So that's the only requirements, and which means that you can use them in really to it's what they call plug and play. So it's great. And just for people who never had the chance to look at these algorithms and how they work, here is just a sketch of how it works. So you have your epidemic curve, and so it's a simulation-based approach. So you're going to simulate n,000 the start of n epidemics, and so each run of the simulation here is called a particle. So you simulate these n epidemics for the time 1, and then you're going to calculate the weight of each of the particles. So and weight here being defined as by your observation model, how close your data is to your model. And you are going to resample your particles according to these weights. So the particles that are inconsistent with the data are going to disappear, and you start again and again. And so you end up basically being able to track the trajectory, the observed trajectory. And that's why these approaches are much more efficient than just doing n simulations and looking at how your n simulated curves fit the data. And the other amazing thing with these approaches is that you have a very good approximation of your likelihood, which means that you can do any sort of model comparison or parameter estimation. So if you look at the literature in SMC, there's really, there's a lot of research going on now, and a lot of very good people working in these areas, which means that we see regularly some, new algorithms coming up. So a few years ago, we had the maximum likelihood iterated filtering of Edionides and Haranking. More recently, particle MCMC, SMC2. So here, I think we should, I'm not sure as a community we are going to come up with the next very clever algorithm for SMC, although maybe Aaron, you will find the next generation. But we certainly need to to monitor what is done in that community and to import all these new algorithms into our field. And also in terms of platforms, you now find some very some great platforms. The R package Pomp and Plum, which hopefully will make easier for people to use these techniques. In terms of limitations and needs for future developments, I think the limit right now is when you start to look at problems of very high dimensions. So these approaches work very well when you fit a model to few epidemic curves. But if you wanted to look at, for example, the measles time series in the UK, where you have few hundreds of epidemic trajectories, I think you wouldn't be really able to scale up the approach, because you would require a lot of particles. So just for computational reasons, that would be very, very hard to do. Also, if you have a model where one simulation takes a lot of time. So, for example, trying to fit an individual-based model to some data, just having to do thousands of runs per estimation of the likelihood would be very difficult. So I think here we should try to explore a bit more. So the balance between these algorithms that are very generic but computationally intensive, like so all the algorithms I presented, and those algorithms that are more problem specific, so you cannot apply them to any problems, but are computationally efficient. So here is an example of that kind of situation where we were trying to estimate the impact of school holidays on the transmission of flu, and so we had an agent-based model with individuals going to school or households, and so it was one run was taking a bit of time. So rather than doing the approach I presented you, where you simulate, let's say, 2,000 trajectories and then you only keep the ones that are consistent with the data, we found a way where we would always simulate one trajectory that would be consistent with the data, and then you just need to apply a correction to your likelihood. So that's just but clearly you cannot use that for any sort of data. The other thing, so in general, so approximate Bayesian computation is the idea where you're simulating n epidemic curves, and then you will approximate your likelihood by the proportion of these epidemic curves that are close to your data. And so close is defined by some summary statistics. And so in general, I don't see a lot of, I don't think it's necessary to use these techniques when you fit to one epidemic curve, just because SMC works so well. But maybe for these situations where you want to fit a model to 200 or 300 epidemic time series, like measles transmission, where clearly we are not going to be able to do that with SMC. Maybe here using approximate Bayesian computation with some well-chosen summary statistics, I think would be relevant. And the last concept, I think, that had quite a big impact in the way we do inference is these three reconstruction methods, which I think really introduced a non-parametric flavor to our field. So work done by Jaco Wallinga here, showing that if you know the epidemic curve, if you know the generation time of the disease, you can somewhat reconstruct the probabilities of who was infected by whom, and from that estimate trajectories of the reproduction number over time. So what's great compared to all the heavily parameterized models is that you're making somewhat much less assumptions about the underlying transmission process. And that's certainly, a different way to look at these time-varying variables, where in the standard way with our, so again, quite parameterized models, we, if you want to change the transmission rate, you don't necessarily have a lot of flexibility in how you do that. You need to say, I'll fix my transmission rate to a certain date, then change it again. And here you don't have to make all these assumptions. But the cost for this increase in flexibility is that you see a very big increase in the variance of your estimates of the reproduction number over time. And so the challenge has then been to find ways to control for this variance. So introducing some smoothing in these estimates. And so a lot of methods have been introduced to do that, but there was, I think, so we can control for the variance, but I'm not sure we were able to find the best trade-off. And I think maybe Joseph Duro recently published that very nice paper in biostatistics, where maybe that's a nice way to think about this problem. So again, it's a sequential Monte Carlo approach where he's so fitting a transmission model, SIR or SCIR, to a flu pandemic in the UK. And what they said was that the transmission rate followed a diffusion process. And they just estimated the variance of the diffusion, and also were able to reconstruct the trajectory of these parameters. So I think it's a very nice way to do it, and certainly also it shows once again the strengths of the sequential Monte Carlo methods. And in terms of moving forward with tree reconstruction techniques, I think very often we would benefit from integrating them in other frameworks. So where if we are fitting a parameterized model to a certain data, we are usually not just interested in estimating a transmission rate, but we also want to say who was infected where or by whom. And once you've fitted your transmission model to a data with, for example, data augmentation techniques, then you can actually reconstruct the transmission tree, and so from that derive some interesting summary statistics. So I think linking often the different approaches is also something we should do more often. So just to conclude, I think we've seen major developments in the way in methods to analyze data, and really often it has changed what we can say about this data. So I think that's great. On the downside, I think very often the epidemiologists who, for example, have collected good data, done an outbreak investigation in a school or household study, or looked at an intervention in a place, and where the outcome is specifically looking at the impact of this intervention on transmission. Field epidemiologists doing that kind of work, I think often they don't have a good sense of how these statistical techniques can actually are directly relevant for what they are doing. And so when we talk to them, often their first view is that so I'm doing my analysis, I'm going to compare the number of infections before and after, for example, and then modeling doesn't enter in the way they think about their data. So I think maybe we have more work to do to make these methods more visible for all the end users of these techniques and those who have data to analyze. And I'll stop there. Thank you.
Thanks very much for this insightful talk. Any questions, comments?
Yeah, that's a very impressive collection of statistical methods. I still think it's very difficult, even for statisticians, given the data and the underlying model, to decide which of these to use. Do I use particle MCMC? Do I use regular MCMC? Should I just try to do some kind of EM algorithm? And I don't know if there's any words of wisdom you can impart to us about how to decide. Because
use a sequential Monte Carlo. No, I mean, my split about this is for any data where you have detailed individual data. So in an outbreak in a school, in a household, I think data augmentation is really the way to, because you don't have to care about when your simulation fit or doesn't fit to the data. It's always fitting the data. Then if it's more time series, I think SMC is the way to look at this data. And if it's more bigger data sets where we can't use any of the two others, then maybe ABC. That would be my easy split between these methods.
Do you see any continuing role for just ordinary maximum likelihood, scoring routines?
So I'm rethinking. So actually, to be more complete about So the big problem when you're doing when you have detailed outbreak data, so data augmentation is great for parameter estimation, but then you're stuck with for model comparison because you don't have you don't have a way to test differences between models. So in these situations, actually thinking about maximum likelihood.
Okay, thank you very much.